Understood. Okay, thank you all for coming. It's a great pleasure to have Nitin Saxena here. I mean, like you'll have to be living under the rock if you need an introduction to Nitin Saxena. So Nitin Saxena is a professor at IIT Kanpur, and he's I would say, an expert in the general area of computational algebra and several mathematical computational aspects of mathematical problems. And among other things, I learned today that he's also dabbling in several AI-related problems as well. There's a lot of demystifying that you can do by talking to him. And today, one such thing is going to be about what is called the border of algebraic circuits.
Yeah, so thank you for coming. And sorry for calling you here on a long weekend, and that weekend of Holi. But that was the only time I had. So I think these slides will be a bit long for 1 hour. If I try to just give you the brief introduction to the problem, the model, and the maybe some proof ideas. And if you have questions, you can ask me afterwards. Yeah, so since I'm saying I'll demystify something, I have to first create the mystery, right? Unless I create the mystery, there is no point demystifying. So I'll define some algebraic models and what is the border of an algebraic model, and then I'll demystify some very small parts of it. So this is joint work with my PhD students, Pranjal, Pratik, and a recent one where Bhargav is also involved. I've given this talk multiple times, but I think the audience will probably not overlap. And also I'll try to simplify some things from previous talks. So I'll give the basic definitions, then I'll define some models, especially depth 3 circuits, the border of that. And then I will basically try to give the ideas of demystification part, which is proving upper bounds. Okay, so this model, how easy is it in terms of classical models? And if we have time, which I don't think we'll have, prove lower bounds in that model also. So the basic model is, which you must have seen in this institute a lot of times, is this computational model where the input variables sit here. So don't think of these variables as taking values. They are not taking 0, 1 values or something. They just think of them as formal variables. So you want to compute a function in the formal variables at once before evaluating it. You don't want to evaluate it. You want to compute the whole of a function as a whole. So this is how the function is computed on formal variables or expressed on formal variables. So you can add variables, or you can add inputs, you can multiply inputs. And then ultimately, after several layers, you will get the answer, which will be obviously a polynomial. Where are the constants? So the constants sit on the wires, and if they tend to multiply. So like the answer of this plus will be multiplied by 1/3. So you can compute you can represent at least any function, which looks like a polynomial. Over some field. Oh wait, I missed the field. So this small f lives in some field. And these are the variables. So for f, small f is a polynomial in big F, which is the field. It could also be a ring, but I think in this talk it will only be usually it will be a field. You can also think of it as finite field. And then n variables. So just think of variables as n variate polynomial over a field.
So the result of this will be a polynomial. But if you look at the space of polynomials, what all will be covering?
Everything. Any polynomial can be written as this tree structure.
With plus minus structure.
Because we just have to multiply and add. So basically every polynomial is a sum of monomials. And every monomial is just a product case. So you can do it in depth too. So depth, so first parameter of this, so for every computational model, there has to be resources that you are interested in. So we are interested in 2 resources. One is size of this. So what is the graph size? We don't care about these constant sizes. We only care about the graph size. So how many vertices, how many edges? So number of nodes plus edges is the size of the circuit, and size of a polynomial will colloquially mean the minimum size of the circuit that computes that polynomial. Because obviously the graph is not unique. So there will be many graphs and you have to pick the smallest one. That also can be many. It's not unique. Minimum is not unique. So whatever, but the size obviously, min size is unique. So that is what size of it is. And depth is how many layers there are. So this I will call depth 3. Okay, so this is the model we are interested in this talk.
And so fanning fanouts can be arbitrary or there
Yes, yeah. There is no restriction. So they will be upper bounded only by the size. So you have addition sigma pi sigma of variables. So which is sigma sum of product of linear polynomials. That's the model for this talk. Just to give you a general picture of this algebraic complexity theory, we call it. So one interesting polynomial in this theory is the determinant. So X sub S is a S cross S matrix with every entry, ijth entry of formal variable. And the determinant of that is defined this way. I mean, obviously, you have seen this before, but simply to remind you the notation. So you go over all the permutations on S elements, and you have to put the sign together with that particular monomial given by the permutation. Okay, so this is a degree S polynomial, and it has S factorial monomials. So although it has exponentially many monomials, the point is still in practice we are able to compute it fast. Okay, so that is because of some magic that this polynomial has. And that ultimately is formalized by a small circuit. There is a small circuit which is able to compute this polynomial. And this is essentially a motivating example for all other problems. We are trying to understand which polynomial behaves like determinant and which polynomial is worse than determinant, exponentially worse, right? We want to do the classification. But determinant itself is a computational model. And the thing that it can compute, we call it VBP. This is variance algebraic branching program model, or I'm calling it here simply determinantal complexity. So DC of a polynomial is the smallest determinant, in which if you substitute in the entries linear polynomials, then you get F. Okay. So you want VBP is defined as a set of basically forget about the sequence. Fn will be called in VBP, and Fn is an n-variant polynomial. If there is a polynomially bounded means that for n variables, you want to look at a matrix which is poly n cross poly. So n to the constant cross n to the constant. That kind of matrix is there filled with linear polynomials in the n variables such that the determinant is equal to Fn. So determinant can be seen as a computational model. And there is a interesting result which is not very easy to prove. It's a interesting theorem which says that determinant has a circuit also. Okay, so determinantal complexity actually is a practical measure for the easiness of the polynomials, because you can actually fabricate a circuit which will be able to calculate this F. But this is a more refined measure here. Determinantal complexity is more refined than just circuit.
And along with computing the function exactly, is a theory for computing an approximative.
Yeah, so this talk is about that. Yeah, but we have to develop many things before we get to that. So, because as I said, we are interested in polynomial, we are interested in computing the function as a function. We don't want to evaluate it. We want to compute the whole function. And then there is an underlying field which also we are ignoring in our measures. So under this setting, we want to define approximation. So it's not very easy, because we are not evaluating. So what does it mean when we say that we are approximating a polynomial? So it's a very algebraic, even algebraic geometric concept, which we will get to later, hopefully soon. So yeah, so I already told you about ABP. That's the next point. So this there is a model called algebraic branching program or iterated matrix multiplication, where instead of determinant, you look at the next best thing, which is multiplication of matrices. Okay, so you can do the same thing. You can have not just one matrix, but many matrices. Each matrix has entries that are linear polynomials, and then you take the matrix product, and you say that in the product, I'll take, let's say, the top left corner polynomial, and I'll say that has been computed. That is my Fn. Okay, so that's another model, and not very surprisingly, this matrix product definition or the determinant definition, they are equal. Okay, there is a major result by Mahajan and Vinay that shows that if you can compute anything fast on determinant model, you can compute it fast on ABP and vice versa. Okay, so they are equivalent. But I cannot sketch those ideas here. It's an interesting theorem which gives a completely, actually when it came, it gave a completely new interpretation of determinants. Okay, that interpretation did not exist before that theorem. What is hardness? So hardness in this area means that the model, computational model that you are looking at, circuit or determinant or ABP, what kind of sizes are you seeing for the number of variables n? Okay, so for a number of variables n variant polynomial, if your model is taking poly n size, then you say it is efficient or small. If it is not, if it is requiring more than poly, super poly, which asymptotically we write here as n to the little omega 1, which means it is not a constant. It's more than a constant. So it can be, for example, log n. Those kind of sizes mean that if the polynomial is hard. And we are always after classifying polynomials Fn into easy versus hard. Easy means poly size, hard means super poly. So do they exist? They exist a lot in nature. Almost anything you will pick will be very hard. And there is a theorem which says that a random polynomial, a polynomial with where coefficients are 0, 1, randomly picked, is already hard. Okay. Or where the sign is picked in a random way, that is hard. So determinant, in the definition of determinant, the sign was of the permutation. So that somehow became easy. But if you pick those plus minus 1 in a random way, then there is no chance that your polynomial will be easy. Because the determinant is actually a singularity in this set of choices. But the problem is that this is not very satisfactory in the area. This random is not explicit. It's not a natural polynomial. So we are after polynomials that are somehow natural. Okay, so I'll give an example of a natural polynomial next, or an explicit one. So it is this. There are no signs. So you remove the signs in determinant and you just look at some of these monomials given by the permutations on S elements. So this is called permanent. This is a cousin of determinant, which is much harder. There is no practical algorithm for this. Neither to compute the function as a function, nor to compute it on values. Okay, so practically, this is a very difficult question. Even over natural fields like real or integers or other rings, we don't have algorithms for this. Algorithm meaning that for S cross S matrix of constants, you want to evaluate the permanent. We don't know how to do that in poly S time. And of course, we don't know how to compute this function as a function, as an algebraic circuit. So the upper bound known is this from the definition is S factorial. And you can be slightly clever, write down an identity and you can reduce it to 2 raised to s. Okay, so permanent's best known upper bound is 2 raised to s, which is still exponential. So we conjecture that that is the correct bound. There is no proof. But we can use this also as a computational model, although it will be completely impractical. But you can say that if I have a function f, which can be written as the permanent of a small matrix, then that dimension of the matrix you can call permanently complexity. Okay, and this I am defining just simply because using this you can define a complexity class called BNP. Okay. So this is what BNP is. BNP is defined as a polynomial Fn. It contains these polynomials Fn, where the permanent complexity is polynomial in n. So poly n plus poly n matrix, whose permanent is equal to this. And the matrix has again entries, linear polynomials. In n variables.
This just occurred to me that Ruby Shiuda result.
Yes.
Does it say that a random polynomial's permanent complexity would also be very high?
Yes, that's a good question. We conjecture it to be so.
Yeah.
Because for BNP, BNP, there is a criterion called variance criterion, which says that if the coefficients are easy, then the polynomial is in BNP. But random coefficients are not easy. So you will expect it to be much further away from VNP.
So that characterization is an even only.
Yeah, so in a recent work, we are making it almost even only. So we can, right now I can claim that it's almost even. But it's not a precise statement. So the conjecture is clear that if you take polynomial with difficult looking coefficients, then it may not even be in VNP. Usually it will not be in VNP, it will be much harder. So so this is the definition of VNP. It's not very important for the talk. What is important is just remember this chain of classes that we have defined, the kind of problems. Okay, so VVP are the problems which you are able to compute, to be precise, polynomials that you are able to compute by either multiplying matrices or by computing a determinant. Okay, so those things are VVP. VP is the first thing I drew, which was the circuit. If your polynomial is computable by a small circuit, and there is a minor condition that degree should also be polynomial. Okay, so circuit is computing this polynomial Fn whose degree is also polynomial. So we are only in this talk, at least we are only interested in those polynomials whose degree is polynomial. So for example, we don't want these kind of things happening. Okay, so we don't want F to be in this family where there are n variables and the degree is going to 2 raised to n. So that has a different name. I'm not going to do that. So all these things will be same with VNP. The degree has to be polynomial, and there has to be a permanent which is computing that. Computing in the theoretical sense, it will still be completely impractical because we don't know how to compute permanent in any way in practice. By the way, if you are aware of Boolean complexity, then permanent sits pretty high above it, sits here in sharp P. Okay, so there is a long sequence of things which will take a whole day to describe, and then comes NP, and P is here, right? So you already conjectured that P and NP are different, and after a lot of work, there are complexity classes which end up with P to sharp P. So permanent is here. It's very hard in practice. In Boolean complexity, it's very high above. The only upper bound you have here is P space, essentially. Okay, so the gap we are looking at is actually from polynomial time to polynomial space. This is very close to polynomial space. Polynomial space contains very hard polynomials.
Everything is conjecture in terms of relationship.
Yeah. In this hierarchy, a part here is called a polynomial hierarchy. It has infinitely many things. Everything is unknown, whether it is proper or equal. In fact, whether the hierarchy is infinite is a conjecture. We don't know whether this hierarchy is infinite. It may also be finite. But we won't be conjecture it to be infinite. That's the polynomial hierarchy conjecture. So this VNP, if you prefer algorithmic style, so VNP contains some very hard polynomials. We're very far away from any practical algorithm. While VP is kind of this part, which is polynomial kind of algorithms. Although this translation is not very easy because of models being very different. So here we do Turing machines, there we do algebraic circuits. So there is some confusion there. These notations here are more complicated than just what we have seen in Boolean complexity. But there is some comparison. So here again we conjecture these to be strict. Okay. These are open questions. In fact, Gradient already conjectured them to be different. Precisely, he conjectured that this determinant and permanent complexities are strictly separate. Okay, so determinant permanent cannot be written as a small determinant. So you have to pay the price of this n to the super constant. And moreover, in the same spirit, we conjecture that VP also is separated from VP. Okay, so in fact, a more refined version is VVP is different from VP, and VP is different from VP. Every part is different. Okay, so now we'll go to the approximation part. Any questions till this at this point? This is the exact computation of a function.
So super constant is just any function that's increasing.
Yeah, it can be anything. So it can be n to the log star n. This is the inverse Ackermann function. Everything is allowed. So we just write, we can explicitly write it like this n to the mu n, where mu n tends to infinity.
Yeah. If I was to select all super functions, they can keep on.
Yeah, it doesn't matter as long as the limit doesn't exist.
So can one say that the infimum will have the same properties? May or may not.
Sorry, infimum of what?
All the functions, like take all the increasing functions and take the minimum of them. That probably will be the
Is the
same.
minimum pointwise or minimum and what's this?
Pointwise.
But pointwise the maximum will become constant.
Yeah, I guess. So.
Yeah.
No.
So there are also other things. We want these functions to be constructible because this actually appears in a count. It is not arbitrary thing. It actually is counting the size, the number of the vertices and the edges in the circuit.
Right.
So this mu n has to be a constructible function. So in practice, these functions are very clear. They are not abstract.
But the conjecture is actually exponential.
Yes.
That n to the omega is actually
Yeah,
sure. So it would be omega.
Sure, yeah. Yeah. My conjecture is actually that it should be 2 raised to n. So 2 raised to n means it should go like this, big omega. So we don't even say 2 raised to square root x. We are actually saying 2 raised to cn, constant x. Okay. So if no questions, then I can move to the border definition. This is a bit tricky, and if you have not seen this, it's completely unmotivated. Part of this unmotivation is that I don't want to go to algebraic geometry. So people who love algebraic geometry, since this is TIFR, we can go into that, but it will take this a longer because I have to set up notations of multiple chapters from basic algebraic geometry. So I'll just do the simple thing. The baby version is given by algebra. So that I can present in one slide. You don't need any further notation. So let gamma be any sensible measure. In this talk, it is either size of a circuit or dimensional complexity or polynomial complexity. And we define border, so we put a bar on that. So bar actually represents closure. Okay, so we call it border, but we can also call it the measure of the closure of a class. Let's say VP bar or VP bar or VNP bar. So we have a bar here for gamma. So we can say size bar or DC bar of a polynomial H. This is the smallest size model which yeah. So this is the equation. So that this equation is satisfied. Okay, so there has to be, so instead of computing H directly as one, let's say circuit, you are allowed to have infinitely many circuits with a formal variable epsilon present. So epsilon is now an additional variable. So now we have.
There's a red button under the yellow cloth.
Okay.
And it will move the board.
Oh, that's very advanced. For a math school. Okay. So yeah, so now we have F, epsilon, and n variables. Okay, so now you think about this. So whatever I will say or do on the slides, this is the universe where it will happen. Because there are n variables which are formal, and now there is another variable epsilon which is formal. Additionally, you are allowed to divide by functions in epsilon. Okay, so you can do things not only like 1 over epsilon to the n, but you can also do things like this. Okay, so everything is any polynomial in epsilon you can divide by. So that's the extra notation that you have to remember, and with that, this definition will be over. So each epsilon is here, and it's in fact, I should not say infinitely many here. I think I'm just saying one. So there is a circuit, or there is a polynomial h epsilon with a small circuit. H epsilon lives here, and when you set epsilon to 0, you will get h. Okay, it is that simple. So instead of h, you compute h epsilon, and the understanding is that if I set epsilon to 0, then I get h. So question is, why is this a different model or a different measure? Right? What is new which is happening? If I'm using epsilon and then setting epsilon to 0, nothing should change. Right? So what changes? So what changes is that maybe in your circuit for h epsilon, so you are computing h epsilon here. And maybe at some point you divide it by a high power of epsilon, and so as a constant, and then somewhere else you multiply it by something by high power. Okay, so you are continuously doing either dividing or multiplying, and then you get this h epsilon. So if you set epsilon to 0, these edges are undefined. This edge in particular is undefined because this is division by 0. So think of a C program. In the C program, you're actually dividing by epsilon freely. So obviously, when you do the division, it is done on the trust that you will never set epsilon to 0, right? So the circuit itself doesn't allow you to set epsilon to 0, but the result, since it is a so I should maybe write one more ring. The result actually comes out here. If the result comes out here, if your h epsilon lives here, so if h epsilon is actually a polynomial in epsilon in the end, then you are allowed to set epsilon to 0 in the end, right? So after everything is computed, then you can set epsilon to 0 and it's allowed. But in the intermediate steps, it's undefined. It's ill-defined, okay? So you cannot do that. So maybe by this additional notation, you can do certain things which were not possible before in the absence of epsilon. Right? That's the definition, and that's also the intention here to somehow use this extra epsilon, which is so now, yeah, analytically or geometrically, there are some 3-4 other definitions which are equivalent to this. I cannot discuss all of them, but you can think of epsilon in real terms as something which is very, very close to 0. Okay, then you can evaluate this. So if you take epsilon to be 0.001, then although it's nearly 0, but still you will be able to evaluate these as constants. And then each epsilon will become each at 0.001. You'll get some answer. And if you keep on reducing epsilon, we go from 0.001 to 0.0001, 3 times 0.01, then you'll get a better approximation of this. So that is the idea of approximation here, that at least when the field is the field of reals, you are not getting the exact function, but you are getting functions with similar coefficients. The smaller epsilon gets, the better the coefficients are.
So, building on what Sandeep was saying, this is giving a sequence of polynomials that is converging to what you want, and every element of the sequence has bounded sets.
Right. Yeah. Yes. Yeah. This graph structure is ultimately, we'll say that like here I'm saying gamma of h epsilon should be less than or equal to s. So the size of this graph is space. This is what we maintain. Yeah, but in the reason why I prefer this algebraic notation, although this is not how it was invented, this thing actually came because of algebraic geometric for algebraic geometric reasons. But then, since we like more explicit things and more algebraic things, so we prefer to use this. Advantage is that I can work with now just one graph. So this h epsilon is a single column. I don't have to think of infinitely many things approximating h.
Sure. So the limiting system somehow is now a richer class. Is that the way to think about this? Like as epsilon goes to 0.
It is richer. It could be richer because you are allowed to divide by, let's say, epsilon to the 2 to the s. because we don't count the constants. So now constants are, instead of f, they are f epsilon. So you can put completely crazy polynomials here, which have degree 2 raised to 2 raised to plus.
I mean, one concrete example is tensor rank. You could have tensors, each with small rank, that are tending towards the tensor that actually has larger. So it doesn't happen for rank of matrices because the limits are already the same. But for tensor rank itself, weird things start happening.
Correct. Yes. Yeah. So yes, I'll give a more compelling example in the next slide. So this epsilon thing actually helps sometimes, and classically we have not been able to improve on those results. Yeah, right. So here is a simple example if you got confused with the notation. So I have two kinds of variables here. I have z and I have x1. So maybe I should put z also here because later in the talk I get z as well. These will be my variables in the talk. So z and x bar are kind of the same variables. So I have here z and x1, and epsilon is a special variable. For border purposes, it is placed there. So you are allowed to divide by that, and you are allowed to multiply by that.
So the first one on the left, the limit doesn't exist.
Yeah, so I am now giving you a definition of limit which abuses what I said before. I mean, I need this because our whole paper actually uses this. It's a clearer way to define limit. So what is done is, actually I wrote it here also, I should have read that. Instead, one simple interpretation is setting epsilon to 0, but a better interpretation is that you want to see everything as a polynomial in epsilon and pick the least coefficient with respect to epsilon. Okay, so like here, you are allowed to have negative exponents also, and then this is epsilon to the 1, this is epsilon to the -1, so you pick this one. So you want to give this thing more importance, and you don't care about what comes after that, or what comes above it. Okay, so this limit of this for me is the same as the limit of this. So you can also normalize this. You can multiply the epsilon, make it into a polynomial. So then you will get epsilon square and epsilon to the 0, and take the least coefficient of epsilon, which is z square x1. Okay, so this goes on in our paper a lot. We have this hidden language we use, but I wanted to put this in the example so that you don't get confused. Originally, you want to set epsilon to 0, but really algebraically, what you want is take the least coefficient.
Dominant.
Is this called? Yeah, in the power series terms, this is the dominant one there. So if you think of analytically power series in epsilon, then you want to pick the dominant one or the residual one or the order one. Order of the power series is determined by the least epsilon. So we want to do that. Or you can also take, so that's the power series in epsilon. This is the Laurent series in epsilon. So in terms of Laurent series, you pick the least one, the dominant one. Yes, exactly. And then you don't care about epsilon, neither will you care about what comes after. Okay, so we, by this or by that, we just mean z square x. Yeah, so that will be important. So many times I will just assume this implicitly. Yeah, so this motivates a new model.
So the question
Question?
Yeah. So in the Laura series interpretation, sometimes it's easier to just hit the -1 coefficient. I mean, like the residue, which is -1.
Yes.
Even though it might not be the lowest or the highest. So does that lead to any kind of
lowest?
Sorry.
So -1 here is the lowest.
Yeah, here it is. But if I had a longer Laura series on both sides.
Okay.
Still sometimes it so the residue is just the -1. So it's somehow easier to
No, that's
get it out.
No. So in Laurent series, the least will exist. It will be a finite number.
Yes, it will be. But I'm just asking for a different model where, like usually the residue, which is the -1 coefficient.
No, yeah. Sorry. So I think I should not use the word residue. Okay. I should just use least monomial.
Okay.
Yeah, just the least monomial or order of the Laurent series.
But that doesn't lead to a different model if you consider the residue itself.
I think it will change everything.
Okay.
If we take all residue in the real sense, then I think there will be a problem, because it will be something very different than what we want. So we want to capture the idea that epsilon is very close to zero.
Okay.
But by being very close to zero, you get information only about the dominant term, not about other terms.
Yeah.
So now you are actually going deeper in the polynomial. That I think is, then you will be computing something which is uncomputable in practice. While here we conjecture that we are not computing something very, very hard. Probably we are just computing maybe. Okay, that is a conjecture. Not everybody believes that conjecture. So we have been working on that so that people believe more. So that is the point of this demystification. Okay, so this was, I think, first time it was given by Björge sir, and he called this approximative complexity, approximative circuit complexity. Note that he did not call it approximation. He calls it approximative because it's not that you want to approximate the value. Okay, you actually want to approximate the whole function without fixing it. You don't want to fix the values. This is a very different notion. And again his guiding principle was this topological notions in algebraic geometry. He came up with this definition of border because of topological reasons. Okay, so this is the new model. So as I said before, on the edges you have these constants which are fractional polynomials. So you can have polynomial upon a polynomial in epsilon. We will not count what we have put. Okay, so you can put here any degree, any constants in the coefficients, and it will not be counted in this sense. And that makes it very dangerous because maybe the degree is tremendous, and at that tremendous degree, it's kind of very, very high precision that you are using in epsilon. So if you use very high precision in the constants, then maybe you can compute more. So that is the danger. So, which is why this model may be computing more than circuits, more than BP. Yeah, so function field is just this, if you did not know that. So polynomial upon polynomial in epsilon. This is called the function field because you can add and multiply and invert here. And so now everything that will compute G polynomial will have n variables and epsilon also. And sometimes this will be a polynomial in epsilon. In fact, I think, yeah, it depends on the context. Sometimes we want this to be a polynomial in epsilon, and sometimes we'll not, because we have also defined the least coefficient notation where you don't worry about this being a polynomial in epsilon. You just extract the least coefficient, right? So this in general can just be a non-polynomial in epsilon, but it is always a polynomial x. Because x are key variables. Ultimately, you only want to compute polynomials in x and not anything else. Okay, so I think this is just working this out a bit more. So, in terms of polynomial, you can just think of what is being computed like this. Expand, focusing on epsilon, and the coefficients are polynomials in other values, x to x. Okay, and what you are interested in is just G0. Right? You only care about G0, everything else is garbage. So the higher order terms are garbage, and just the least coefficient, which is G0, is what you wanted to compute. That is what you say I have computed in the border model. So that's the guiding question. How easy is G0 in comparison to G? Right? So G has a small circuit. Does it mean that G0 also has a small circuit? So yeah, these things I've already discussed. So you cannot just blindly put epsilon to 0 because there are problems inside the circuit. Division by 0 that happens. So bottom line is that perhaps this notation is approximating the circuit G0 in a highly non-trivial way. Okay, this is not so easy to understand. It may be, to eliminate epsilon, it may not be easy. Right? This needs more investigation. The definition is meaningful. Any question? Okay. So yeah, so that's the, so now I can define the error polynomial also. So if you want to write it, see the connection exactly between G and G0. So G is on the left hand side, which is what the circuit is computing in a small size. And if I ignore, or if I look at the least coefficient with respect to epsilon, that is H. And this is the polynomial I was interested in originally to compute. And whatever is contained in multiples of epsilon, that is the H. That S is called the error term. This is the error polynomial. Yeah, so it is important to say that when we say size of G, we mean size over the constants being the function field, not size over the original constants, because that size can be incredibly large, right? Because we have these big polynomials sitting here, so the size of these can be exponential, super exponential, whatever, doubly exponential. So you don't want to count those. So the size over the constants being the new constant, the epsilon function field. And yeah, then we call H this thing to be of approximative complexity S. Right, that's the definition. And when you want to go from G to H, you just take the limits, with the limit iteration being defined as before, totally algebraically. So what can you say about the degree of S, this error term? How big degree? Well, is it true that if I keep increasing the degree of S, maybe I can keep computing more and more, stronger and stronger, harder and harder polynomials? Okay, so that is theoretical. That was a theoretical possibility, but Lane-Poole-Lichtide, again using algebraic geometry, gave a theorem which Birgisser uses in his papers to show that you don't need degree to be more than 2 raised to s squared. So simply put, there is no advantage if you take functions in epsilon here that are super exponential degree. Okay, so whatever good you can compute, which is h, you want to compute h. So whatever h you want to compute, which is say of degree s, you only need to go for epsilon degree exponential in s. Okay, that's a highly non-trivial theorem because in the definition, by the definition, it doesn't say anything about degree of epsilon. It could have been anything, or it could have been infinite.
So 2004 is when this architecture approximation
Correct.
started.
Yes, yeah. Peter Birgisser did this in 2004, defined this, and yeah, I will give you the motivating problem. That's another interesting problem in circuits and algebraic algebra. But to solve that, he needed to define and work out this model. And then there was some bug in the Lane-Poole-Lichtide application, which he has corrected recently. It's not very important. So in one line, the proof of this is, I mean, if you know the Zariski topology, you just use Bizu-Hegel theorem there. Okay, so the topology which is important in my definition is the Zariski topology. It's a bit different from, I mean, it's completely algebraic, and it's a bit different from what we do in real analysis, which is drawing spheres and intersecting them. So we are not doing that. Because there may be no spheres to be drawn. Right? If F is a finite field, how do you draw spheres? There is no metric, there is no notion of distance between, let's say, 0, 1 and 3 mod 5. There is no good metric there. It doesn't exist. So you want a topology which doesn't depend on metrics. So that is the Zariski topology, and there you use Bizu-Hegel theorem in that geometry. So that will give you this. Yeah, this part I'm completely skipping. You can, if you are highly interested in this, then you can talk later. Yeah, this is again the same thing you can do. So once you know that epsilon's degree goes only up to m, then you can, to extract G0, you can do interpolation. Because epsilon is after all a formal variable. You can just evaluate epsilon at m plus 1 values. And you can get not only G0, but all the GIs. Right? So that's both a boon and a curse. Because originally the definition only cared about G0. If you use interpolation trick with the degree bound, then you will actually get all the GIs. So that is doing too much. And obviously it will not give you a result because degree m is 2 raised to s square. So this is just saying that G0's complexity or H's complexity is exponential. Although G was polynomial, right? So the gap you are getting is polynomial to exponential. This is not a result.
So you mean it's a boon method in the sense that if we wanted to hope that that m is actually much smaller, then we will also have to admit that we believe the other GIs are also
Correct.
easy.
Yeah.
Probably don't.
Yeah. So this is actually tying all the GIs together.
Which we probably don't believe is.
While the definition wants to treat all the other GIs as garbage. So we don't want to prove any property of GIs. We only want to prove a property of G0. Right? So this interpolation and degree bound is not sufficient. This seems too big a hammer to understand approximative complexity. Yeah, so that's the gap. Size of a polynomial in the classical sense is upper bounded size of this. So that h only next is upper bounded by the exponential of approximative size. And obviously, approximative size is less than or equal to classical size because approximative size also has the field f inside. So this is the trivial part, and this is highly non-trivial. Okay, so I think I don't have much time, but I still want to discuss this. This is the curious algorithmic algebra question which Jürgensen wanted to solve, and for which he designed all this machinery of approximative complexity. So this problem is that if I give you a circuit, or if I have a polynomial which has a circuit of size s, okay, but the degree of the polynomial is maybe exponential, maybe 2 raised to s. Okay, so an exponential degree poly-size polynomial f is given to you. What can you say about its factors? So this is the factorization problem of polynomials. So do polynomials that have small size also have small size factors? It has a factorization problem, so he wanted to solve that. It is in those days it was already solved due to results in the 80s, sequence of results when the degree is poly s. So he wanted to solve it when the degree is super poly s, like 2 raised to s. Okay, so exponential degree and small size. So if you are seeing this first time, you will not realize it, but all you have to focus on is factors of low degree. Because if you want to study factors of exponential degree, they again can be very hard. You will not get a result for them. In fact, you can give counter examples where the high degree factors of high degree polynomial are exponentially hard, even though the original polynomial f had a poly-size circuit. Okay, so it doesn't work for all the factors, but it does work. I mean, so what Wilberser showed was that if you only focus on small degree factors, degree f factors of a polynomial which has size s circuit and 2 raised to s degree, these small degree factors are possibly also easy. This is what he showed. So easy, we obviously conjecture it to be in VP, but that's an open question. Wilberser showed it in VP bar. So this is a kind of a practical problem which approximative complexity solves. It actually tells you that the low degree factors of high degree polynomials are easy in the approximative sense. They are in the border. Okay. In other words, in the border measure, low degree factors are there, but in the classical complexity, it's an open question.
So this is also sort of assuming we don't expect that hard polynomials will become approximatively easy. So you said the reason we only care about small, like talking about the approximative complexity of lower degree factors is because we can create examples where
Yes.
higher degree factor will
be hard.
conjectured to be hard.
They will be hard, yeah. Actually, the proof is not that difficult, so it's just a counting argument. So if you have a degree 2 raised to s polynomial, and you count the polynomials which are, if you just count the factors, they will come out to be, I think, super exponential. So there are super exponentially many factors. So one of them has to be hard. Or in fact, most of them are hard. So you cannot make a statement about all the factors because there are way too many. But you can still make a statement about or conjecture about special kind of factors, in this case, degree S or degree poly S. So yeah, in this case, recently we made some progress with Bhargav. We weakened the notion of approximative complexity to something called presentable border. And then we showed in general for presentable border that these factors are actually in BNP. Okay, so this also was not known before, that these low degree factors of high degree polynomials, are they at least explicit? For all you know, they may have been much harder than BNP. Okay, but that is not the case. So we can actually show over finite fields that these factors are actually in BNP. So there is some evidence that it's not completely crazy, but still BNP is very far from BP. So we have a long way to go to show that. So this is called Buergesser's factor conjecture. So we are still far from proving Buergesser's factor conjecture. Some progress is there. So how much time? 10 minutes, right?
We have about
5 minutes.
Yeah.
Oh, so then I won't be able to give you the main results. So we just ended the preparation. Okay, so depth 3 circle, I've already said it's just sum of product of linear polynomials. So it looks like this: sigma product of Lij's, where Lij are linear polynomials, and we will assume them to be inhomogeneous. So they will be a constant term also. They all come from the base field F. So you can ask, you can now study them via small k. Okay, so how many products are there? So if you have just one product, then it is called sigma 1 pi sigma. And it's very easy to study that. You will not get any interesting result. Next challenge will be when you take two products. So you have one product of linear polynomials, another product of linear polynomials, and you are just summing them. So what is this model? What can it compute? Okay, so for example, are they universal? It turns out that they are not. For example, they can't even compute this silly polynomial. So just inner product of three-dimensional vectors can't be computed. You cannot express this sum of three products as sum of two products. Okay, classically, this is not possible. It's a easy proof. Do have homework exercise over Poli. So this is the impossibility result. So it doesn't matter how many Lij's you multiply, because that is the only thing you can vary. You can just have more and more linear polynomials in the two products, but it will not help. Okay, it will not be able to compute this inner product. Now that changes when we look at the border. Okay, this is a very interesting thing with border, that already in sigma 2 pi sigma bar, when you start approximating, you can actually approximate that inner product, which was not impossible in the classical version. So there is a proof which was given by, thanks to DIFR, which I will skip. In fact, okay, I'll skip that proof. I'll just state our main result. So that was the motivation. So what we show is that any polynomial which is, so see, first thing we have shown is that, or we were aware of, because of, wait, it's not our result. This is just Kumar result. Yeah, so the first thing that we want to make this study meaningful is the model we are studying that should be universal. Right? Because if it is not universal, then it is not even computing all polynomials. So then we are not too excited about that. In this case, it is actually universal thanks to Bilal's result. So what this result says is that arbitrary polynomials are computable in order of sum of two products. And the price you have to pay is in how many linear polynomials you multiply. That grows exponentially. Okay, so you can, which is highly counterintuitive. So you want to compute degree D polynomial, but for that, if you multiply 2 raised to D many linear polynomials and another set of 2 raised to D linear polynomials and add them, everything will somehow magically cancel out and give you degree D polynomial P. Okay, so it's very counterintuitive. There is something very strange that happens with border, which is making this possible. That you increase the resource of degree exponentially, and then you are able to approximate a low degree polynomial P. Yeah, so that is good for us because now the model is universal. Next thing we'll ask is, can we remove this bar by going to, let's say, DP? Right, so is this polynomial, if a polynomial has a small sigma 2 pi sigma bar circuit, then can I make it exact? Can I also say that there is a small circuit, classical circuit that computes it? That is the debordering result we have.
No, not for two, because two you just.
For 2 also.
No, but just didn't you say that for two?
No, so this is the construction of this model for a given polynomial P. Now we are asking the opposite question. Suppose a polynomial P is computable by size S. This basically it means that I am multiplying only S linear polynomials 2 times and then adding them. What can I say about the circuit size, the size of P? Circuits of P or branching program of P or formulas of P. So that's the opposite question.
What Algebraic said that you can't show, of course, that this is going to be like just a debordered exact thing. It's not going to be in sigma.
No, he's going to, that's what I asked.
Higher,
But even then, I think the other thing to also note here is that you only know that the top-fanin is constant. Even the border size is exponential.
No, I understand, but I was thinking when he said deborder is to completely remove the bar. That is impossible.
Then I would have called it closure result.
Because sigma 2 pi sigma just is said is not.
No, he's giving an upper bound for a border class within VP. So you want
within
to.
VP. So,
Yeah.
so it's no longer sigma 2.
Yeah.
I mean, the top fanin sigma, that's not good.
Yeah.
Yeah. If it was sigma 2, then I would have said that we have a closure result. That sigma 2 pi sigma is closed under bar. But that is not the case because we just have a simple example. That's impossible. But other things are possible, like maybe this is contained in sigma 3 pi sigma.
So you want to make it as
close to sigma 2 pi sigma as possible.
Yeah.
And the closest we have got is VVP. That is our mean result. Not below that. And also in the later section, the lower bound is that there are polynomials in sigma 3 pi sigma bar, which this bar cannot compute unless you pay a price of explanation. Okay, so there is also a lower bound result. So you can just look at a hierarchy of these sigma k pi sigma bars, and that is exponentially separated. So we have both this upper bound result, that's the debordering result, and second is the hierarchy result. It's a strict exponential hierarchy. For which, for sure, I will not have time for any of this. So let me just skip Reynolds proof. It's a Q proof, and go to our result, which is this. So the border of poly-size depth 3 top-fanin 2 circuits are easy. By which what I mean is that this is in BVP. Okay, so if you have a poly-size, which just means you multiply poly S or poly N D many linear polynomials 2 times and add them, and you are computing you're approximating your polynomial, then it means that your polynomial is already determinant or branching closure. It's in BVP. Okay, so which is classical. There is not approximation. So we are debordering or we are de-approximating. We are making it exact. Okay, so this is the result, like first of its kind, and the proof is a bit too much. So let me, and of course it will also work, we extend it for all constants. So it's sigma k pi sigma bar, same thing. It's in the, so it works for any constant top-fanin. So historically, this constant top-fanin depth 3 has been of interest. There have been lower bounds, there have been identity testing algorithms, and there has been a lot of interesting incidence, geometric or algebraic combinatorics, which people have done on these identities. This is an interesting model, but the border part requires something completely new. We are not able to use any of the previous techniques which existed for exact depth 3. So what we do is, the grand idea is that we want to reduce k equal to 2 to k equal to 1 by hook or by crook. And I really mean this, because when you look at the proof structure, there is really no motivation for what we are doing. So we just wanted to. So this is the only meaningful thing, that you have T1 plus T2 approximating your polynomial f. Okay, so I just put it as a limit. So you have a product of linear polynomials, another product of linear polynomials, and their sum tends to f under this epsilon equal to 0 notion. And what we want is that we want to kill this T2. Okay, we want to reduce it to, let's say, something like S1 tending to F. So the advantage with just one product will be that then there is a very simple or almost trivial proof that if you have a product of linear, if you have f in sigma 1 pi sigma border, then it's already sigma 1 pi sigma. Okay, so you can remove the, basically sigma for k equal to 1, it is closed under approximation. So, I mean, obviously when I say it like this, it's impossible, this cannot work. It can't be that sum of two products reduces to just one product, and that too exactly. Okay, that cannot work, so there has to be some catch. But this is what we want to do in the beginning. We want to solve this by hook or by crook, go to k equal to 1. So what happens when we use this crook style? So the crook style will be following. What we will do is, we'll forget the map for now. Let us just look at this equation, because the other things are too much. So we have applied some like generic kind of transformations to make things in T1 look good. T1 is a product of linear polynomials. You want some of these linear polynomials to be nice. So we have applied some map. Forget this map 5 for now. What we do, the crooked thing that we do is we divide this whole equation by T2. Okay, so we get T1 by T2 plus 1. And then when we see a plus 1, we differentiate so that it is killed. Okay, so we just divide and derive. That is our crooked proof idea. So when we divide and derive, then what happens is I am getting a single object, which is essentially the derivative of the ratio, tending to derivative of almost what I wanted. It's not the original f, but it is a ratio of f and t2 and differentiated. So if you kind of ignore this rho z and this division, then I have a single product of linear polynomials which is tending to it. Because this epsilon part is garbage, which is the error term. Right, and then from here on we use the property of this product of linear polynomials divided by product of linear polynomials. Okay, somehow the border of this is very nice. It's the complication happens because there is also the differential operator. The differentiation is happening here, which is in a new variable z. So that also phi introduced. Phi introduces a new variable z. So because of the difference, so it is the when you differentiate a product, you get something slightly more complicated than a product. But derivatives are nice, somehow they make things work. So I think I'll just stop at this because other things are just way too technical for a late evening in a long weekend. Next one, actually, I can show the lower bound result. Yeah, so the lower bound result is the following. For any constant k, what we show is there is a very simple polynomial in sigma k plus 1 pi sigma, which if you try to calculate by sigma k pi sigma bar, approximated by sigma k pi sigma. So it is similar to the inner product idea. Three products you cannot compress into two in the classical world. Here, what we are showing is that k plus 1 products I cannot compress into k products even under approximation unless you pay a price of exponential. Okay. So that proof was trivial. This is highly non-trivial and very complicated because we actually have to deal with this issue of already sigma 2 pi sigma bar being universal. It can compute anything. So we actually have to show that Vinal's construction is by chance optimal. Okay, nothing better can be done. It actually requires exponential.
So this is not trivial even for k equals 2, right?
It's not, yeah. So all my proof ideas are for k equal to 2. Yeah, k greater than 2, I will not even dare present in a talk. Because I never finished k equal to 2. So how can I go to k equal to 3? So k equal to 3 has some other crazy things going on. But the level of them is not as high as k equal to 2. So k equal to 2 really needs many new things. K equal to 3 is just laboring and digging the hole deeper and deeper. So, okay, so actually I can show the polynomial. It's very easy looking. It's just PD is just this thing. It has so k equal to 2 is fixed. So for there are three products, and each is degree d, and all the variables are different. Okay, so this it's kind of generalized inner product. And this you cannot, when you try to compress it into sigma 2 pi sigma bar in the Vinal style identity, then we show that necessarily it blows up to 2 raised to d. Okay, it requires exponential. So it is computable, it can be approximated, but then the price is exponential. Okay, so that identity is optimal, and this works for any k, so we get a exponential hierarchy. Okay, so this proof is being skipped, and yeah, so all our proofs actually, which I skipped, they use something which was done for read-once algebraic branching programs over the last 10 years or 20 years. So that ROABP machinery we use, and that also gives us identity testing algorithms. Okay, so we actually get hitting sets for all these models. So this is not just lower bound, upper bound, but also identity testing. You actually get algorithms. Open questions are, we want to deborder in, let's say, formulas or even in depth-3. Okay, we conjectured this should be possible, but our methods completely fail because our methods are tailored. I mean, they are tailor-made only for constant k. So we are unable to analyze the super constant k cases.
But this we don't even know for constant k. Like even for k equal to 2, we don't know in this containment case.
Yeah. So that is the correct description. Yeah. So it's not, yeah. So even for k equal to 2, so sigma 2 pi sigma bar. Yeah, we don't know how to, actually, it's a different problem. We don't know how to get rid of this algebraic branching program. We want to make it into a formula. But there are the main reason why we are not able to do that is because we are using this ROABP machinery. And ROABP machinery is actually a branching program machinery. It's not a formula machinery. So as soon as we use ROABP, we get into AAP. So we only get BAP. We don't get BF. Yeah, that's one thing. Other question is, what is the border of sigma pi sigma? Sigma pi sigma bar, we don't understand because our methods are only for constant. Some variants of this k equal to 2 is instead of taking products of two linear polynomials, you can take product of matrices, which is basically what ROABP is, and then ask about the border of that. What is sigma 2 ROABP? Approximation. This we have no idea. I mean, we are very far from this. Although we do understand the exact case, we don't understand the border case. There are many results for sigma 2 ROABP, but there is no understanding or no tool for sigma 2 ROABP. border. Yeah, so the other more general question is kind of the overarching question in this area is what is BP bar? What is it that approximative circuits are computing? We don't even know whether it is in BNP. Although I conjecture that it is equal to BP, but we don't even know. We don't have a proof method to show that BP bar is in BNP. Okay, so we don't know whether approximation is explicit. We have no explicitization way for approximation. So we did that for some interesting cases in this recent work. As I said, this presentable border of BP we have shown is in BNP. That's a special kind of approximation. And that solves the problem of the case of Burgess's factor conjecture. We show that these low degree factors of high degree polynomials, they are in game. They are explicit. So thanks.
Questions?
So, point number two, like Prasad was saying, for sigma 2 bar, pi sigma, you still don't know, right? Whether it's in VL. Yeah. So, suppose my original polynomial is multilinear. Is it known that it's in, if I am computing a multilinear formula, it can be computed by, sorry, if I am computing a multilinear polynomial, it can be computed by multilinear formulas?
It's a very good question. I think Pranjal once asked this, but we don't know what to do because, again, the basic technique we have is this ROABP code. So this I couldn't show, but deep inside our crooked idea, the Hooker-Crook idea, deep inside it actually gets out a ROABP. And then since we understand ROABP, so we get happy and we apply all the theorems of ROABP at that point. And then it bubbles up all the way to sigma 2 pi sigma bar. So this ROABP, you can consider it to be multilinear, but it will not help. It's still a product of matrices where AI is just a linear matrix in Xi. But this is not something very special.
But what is your sense? Do you think that it would be in VF?
Oh, no, we think that it should be in sigma by sigma. That's the conjecture.
Like even for multilinears, it would maintain multilinearity. Meaning, suppose I'm computing a multilinear polynomial this way.
I see.
Would you be able to compute it by sigma pi sigma multilinear?
I don't think.
That seems too optimistic.
I mean, because we actually don't have too many examples where the degree in epsilon is actually large. So the interpolation idea would typically work.
Oh.
So that will just maintain multilinearity, everything that you want. It's just we don't have too many examples where that degree is too large.
Yeah, that is a good point. Yeah, so the motivating problem of Burgess was this factorization, but this is a very hard problem. This has nothing to do with simple things like depth 3 or depth 4. This is, you're talking about, since your polynomial is exponential degree, you are necessarily talking about super polynomial depth. So these kind of things happen when the circuits are complicated. Yeah, in depth 3, depth 4, we have no good evidence. Whatever examples we had, and I have many such examples in older slides, they just make the fanin from 3 to 4 or maximum k to k plus 1. So they don't give you a significant gap between approximative and exact models. So just small changes there. So certainly expect epsilon degree to be poly. But since the original result using Lake type is by algebraic geometry, it doesn't care about any of our models. It only cares about a polynomial system where polynomials are general and the variety is general. The topology is a topology. So we can't really hope to use those methods in computational models. Something else has to be done.
Any other question? Okay, then let's thank Nitin again.
Thank you. Question from there. If there is a chart, then it would have.